Alright, gang, here we go. Here's Chem 2, Unit 11. We're talking about thermodynamics. It's been a while since I made a video, which is pretty exciting. But so it's time to record some new content. So in this unit, we're going to be talking about thermodynamics, learning about how energy changes as you have chemical reactions. We're going to really be building on what we learned back in a previous unit when we talked about thermochemistry. So try to dredge up all that information that you may or may not have forgotten about enthalpy and reactions and all that stuff, because everything there will be important as we move forward here. So here we go. Chemical thermodynamics. All right. First law of thermodynamics. Okay, not a biggie, but very, very important regardless. Energy cannot be created or destroyed. The first law of thermodynamics. Energy cannot be created or destroyed. Okay, therefore, when the Big Bang happened, there was a certain amount of energy in the universe, and that amount of energy is all of the energy in the universe from then on forever. The total energy available in the universe is constant, and this kind of leads us to the idea of the entropic heat death of the universe. If there's only so much energy if there's only so much energy, right, and the universe is constantly expanding, then that energy just keeps getting more and more and more spread out until the point where the energy is so far apart from one another that nothing interesting can happen anymore. But that's a topic, that's somebody else's problem, like 1.5 billion years from now or more. All right. But anyway, so energy though, so it can't be created or destroyed, but it can be converted from one thing to another. And then it can also be converted from the system to the surroundings, surroundings to the system, etc., etc. Remember, we talked a lot about this when we were talking about thermochemistry. Is the idea is like, okay, if you imagine whatever you're looking at, we define this as your system. Everything else in the entire universe is the surroundings. And most of the time, when we talk about thermodynamics, thermochemistry, anything like that, we really care about what's taking place across this system. Just to recap, remember anything that's leaving our system is as considered negative. That's my little negative sign. And anything that's entering our system is positive. Okay, so remember that notation. That's important just to keep your math straight. Otherwise, you'll get wrong answers over just silly things. Just remember that notation. All right. Enthalpy is something we spent a lot of time talking about. Remember, enthalpy was our delta H. We talked about lots of different ways to calculate enthalpy back in unit 5, 4. I honestly don't remember. Okay, and then the new guy here. Okay, the new guy in town is our entropy, which is S. So when you see a big capital S, that's your entropy. This might be your first encounter with entropy. So here's like the very, very, very bare bones definition. Entropy is like a measure of the randomness in a system. So you have a system and you're measuring how random that system is. That would be considered entropy. Okay, and here this third bullet point kind of gives you a sneak peek to what this whole chapter is about. We're using those two values, the entropy and the enthalpy, in order to determine whether or not a process is spontaneous. And specifically, because this is a chemistry class, this process that we're talking about are chemical reactions, right? So by the end of the unit, your goal is to be able to use entropy and enthalpy in order to figure out whether or not a chemical reaction is spontaneous or not. Okay, well, what does it mean to be spontaneous? So that's kind of what we're at here. Okay, so if we have a spontaneous process, okay, a spontaneous process proceeds without any outside assistance. So here, this guy has lifted up a couple of eggs. Right here, I'm gonna move my head up here so we don't block this beautiful picture. Okay, and so notice that these eggs are up here. He picks them up and then he lets go and they fall. Right, and then that would be a spontaneous process. Having the eggs reverse backwards and come back up to their hand, that is non-spontaneous. That isn't going to happen on its own. Yeah. So anyway, and that's really what spontaneous and non-spontaneous means. Spontaneous things happen on their own. Non-spontaneous do not. You have to put in some sort of work to make it happen. All right, now a couple of things that are confusing. Don't confuse spontaneous with fast. Okay, just because something's spontaneous doesn't mean that it happens quickly. It just means that it happens on its own. Okay, a lot of times they're synonymous, but not every time, right? So think about rusting. Okay, rusting, if you leave a piece of iron out in the weather, it will rust on its own. Okay, but that is not necessarily a very fast process. It takes several days, weeks, or years, depending on what kind of iron it is, what kind of environment it's in. I'm thinking about the Topeka Capitol in Kansas, the dome over the Capitol. That's made out of copper. When they originally put that on the Capitol, it was this nice bronze colored, and then over time it became copper oxide, right? It rusted. It took many, many years, and then now it's the very green color, okay? And then the other one is don't confuse non-spontaneous with impossible. Okay, so like you might be looking at it as like, well, this is impossible. Yeah, I'd argue that this is impossible without the time stone, right? But regardless, this isn't, not all non-spontaneous processes are impossible. You can have non-spontaneous processes happen. You just have to put some sort of energy in to make them occur. All right, I'm going to drag my face back over here. Okay, so we can affect our spontaneous processes by using experimental factors. So here they're using temperature and they're using temperature to either freeze or melt this water. So here's this water. You got the same amount of water on both sides. I think it's interesting to note that the water expanded as it froze, right? That's an interesting property of water. But so look, if you raise the temperature above freezing point, then it will spontaneously melt. If you lower the temperature below the freezing point, then it will spontaneously freeze. Now, obviously, we can make water freeze at room temperature. We just have to put work. We have to do work on that thing, right? I have to put it in my freezer, and then my compressor and the cooling coils and everything else has to work together in order to lower the temperature around it to make it be in a situation where it will spontaneously freeze. All right. So anyway, so we can use temperature and pressure to affect our spontaneity. All right. Last couple of vocab words here that you need to be aware of here. I'm just going to permanently move myself up here. Reversible and irreversible processes. Okay. Reversible processes is where the system changes so that the system and the surroundings can be returned to the original state by reversing the process. Okay. All right. So essentially, if it is a reversible process, that means if you can undo what you just did, okay, without it losing any energy or anything like that. So here's our system and their surroundings, like that box that I drew at the beginning, okay, and so this is heat change going from the system, which was at a higher temperature, okay, is losing heat to the surroundings. All right, and in order to make this a reversible process, then it has to be small increments. It has to go very slowly. And what this allows is that it maximizes the work done by the system on the surroundings, or vice versa. So surroundings on the system, like was what's going on here. In an irreversible process, okay, you cannot undo the work, okay, by simply reversing the change to the system. Okay, it will not flow backwards. So here, they've removed this piston, okay, and this gas has filled this container. They can't just simply put this back down in order to get back to the original case. They'd have to use this piston to put work in order to get it back down to the same compression as before. All right. I wouldn't get, reversible, irreversible processes are important, vitally important, especially if you go on to study engineering, mechanical engineering, and then thermodynamics. Also, they're really, really important things. But it's not terribly important for where the rest of the unit is going. It's mostly here just to put the little bug in your head, so when you hear it in more complex cases in future classes, that it doesn't catch you completely off guard. All right, so let's do one practice problem. All right, here we go. It says identifying a spontaneous process is to predict whether each process is spontaneous, as described, spontaneous in the reverse direction, or at equilibrium. So part A says water at 40 degrees gets hotter when a piece of metal heated to 150 degrees is added. Well, if we just think about just logically what would happen if I had water at 40 degrees and I put a 150 degree piece of metal inside of it, that water will get hotter, right? That energy from the metal will flow into the water. So A is just spontaneous, right? And see how we can just kind of use logic here just to, and our own gut instinct of things that we've encountered in life to kind of understand what the heck's going on. All right. Part B says water at room temperature decomposes into hydrogen and oxygen. Well, I've never seen that happen, right? If I've got a bottle of water out here on my desk, it is not bubbling into hydrogen and oxygen. If I want that to occur, if I want this reaction to occur where my water is going to turn into H2 and O2, right? I would have to run electricity through it, right? I'd have to do something to this water in order to make this occur. However, go in the opposite direction, that does spontaneously occur. So it's non-spontaneous as written, right? Non-spontaneous, right? But the reverse reaction, right? H2 plus O2 yielding water, and I know these aren't balanced, please don't hate me. This would be a spontaneous reaction. This is spontaneous, okay? All right, let's see. So, and then the last one, benzene vapor, all right, C6H6 at 1 atmosphere, condenses to a liquid at the normal boiling point of 80.1. Well, that would be a spontaneous process. Since they're at the boiling point, right, at the normal boiling point, and normal means 1 atmosphere, that means that vapor will spontaneously, all right, spontaneously turn into, it will spontaneously condense back into the liquid phase. All right, and so that's it for this first bit. We learned about the intro to thermodynamics, first law, spontaneous processes, and reversible and irreversible processes. All right, do your practice problems, do have lots of fun, and I'll see you on the flip side.